In this video, we'll start a study of infinite series. First, I will give you the definition of an infinite series. I'll tell you what does it mean for a series to converge, and then I'll give you a few important examples. Well, what do I mean by an infinite series is basically an infinite sum. So given a sequence a(n), I can take its terms and start adding them up. I could denote this infinite sum by this symbol, the sum of ak, with k going from 1 to infinity. Well, of course, we cannot just add up infinitely many numbers, so we have to make sense of an infinite sum like this, and for this we'll have the following definition. We'll say that an infinite series, the infinite series, that is the sum of ak with k going from 1 to infinity, so adding up all terms in a sequence, converges to the sum, and well, let me put some quotation marks around the word sum, as if the sequence of partial sums and what I mean by partial sums is this sequence when we add up the terms in the sequence ak from the first term only till the end term. So this is just a final sum. This is just the sum of n numbers. So I'm not going all the way to infinity. I'm just taking the first n terms. I've formed this new sequence Sn, and if this sequence of partial sums converges to the limit S. Okay, so this is what we mean by this infinite series having a sum S. It means that we chop off the infinite series after the first n terms, and we'll of course take the new sequence of partial sums with more and more terms and see where that sequence of partial sums tends to. If it has a limit S, we say that this infinite series has the sum S. So converges to the sum is our new expression, and we say that this happens if the sequence of partial sums Sn converges to the limit S. Now, of course, it might not be the case that the sequence of partial sums is a convergent sequence, so we say that the infinite series is divergent if this sequence of partial sums has no limit. So we say that the infinite series is summing ak with k going from 1 to infinity is divergent if Sn, this sequence of partial sums, has no limit. So if the sequence is a divergent sequence, we say that the series itself is diverges. And of course, this could happen in many ways. So it could have no clear behavior. So it could, but it could also be the case that Sn diverges to plus or minus infinity. If Sn diverges to plus or minus infinity, we say that the infinite series itself sum ak with k going from 1 to infinity diverges to plus or minus infinity. Okay, so it's all dependent of this behavior of sequence of partial sums. So these are our new notions. Let me give you a few important examples of infinite series. So my first example is the following infinite series. We'll take a real number q and add its powers starting from the 0th power. So in this case, there is a different starting index. It's the 0 term that we are start with. This just means the infinite sum of this geometric progression. Okay, so you see what's going on. So this is called the geometric series. So this infinite series is called a geometric series. And you might remember from an earlier video, way back when we did proof by induction, we have looked at the following sum, which is exactly the nth partial sum of this geometric series going from 0 to n with k of q to the power k. So this was exactly the sum that we had a nice formula for. And what did we have? Well, if you remember, we had two cases. We had the case when q is not equal to 1. In that case, we could write that 1 minus q to the n plus 1 is divided by 1 minus q. So that was when q wasn't equal to 1. And the other case was simply n plus 1, and that happened when q was equal to 1. Of course, that makes sense, adding up n plus 1 many ones. That was the second case, but the first case was more important. When q is not equal to 1, we had this nice compact formula for this geometric, for this sum of geometric progression. And this is exactly the nth partial sum of our geometric series. So we find that if q has an absolute value that is less than 1, then this sequence of partial sums will converge to a number. Then the limit of partial sums as n tends to infinity, Sn will converge to, well, let's look at this expression, 1 minus q to the n plus first power. Q to the n plus first power as n goes to infinity is going to converge to 0. So let me just write this as 1 minus 0 divided by 1 minus q, which is 1 over 1 minus q. Okay, so this is exactly the sum of our geometric series if q is between -1 and plus 1. So let me write it in this nice way. So the powers of q from 0th to infinity is equal to 1 over 1 minus q, again, provided that q is between -1 and 1. If q is outside of this region, then this infinite series, that is the geometric series, will diverge. Just think about it. Think about the cases when q is equal to 1, it would diverge to plus infinity. If q is equal or greater to 1, then it will diverge to plus infinity. We are adding up bigger and bigger numbers. If q is less than or equal to -1, it will be divergent. Okay, so let's test your understanding. So what I would like you to do is now to use this formula that we have here for the geometric series, and I will give you an infinitely repeating decimal, 0.1055 infinitely repeating, meaning 0.1055, 1055, 1055, and so on. And I want you to express this number as the ratio of two integers. So I want you to turn this infinitely repeating decimal into a fraction of two integers. Okay, pause the video, think about it, and if you can figure it out, enter your fraction in the box below. Okay, so I hope you paused it and thought about it for some time. So this infinitely repeating decimal can be expressed in the following way, and this is basically the idea. We have these infinitely repeating segments of our sequence of decimals. So what we can do is we can write that this is 1055 times the following sum, 1 over 10,000. If you think about this, what this means is 0.0001 multiplied by 1055 would give me just this number. And if I take powers of 1 over 10,000, with k going from 1 to infinity, I would exactly obtain this expression, this number. Well, here we can recognize that we have almost a geometric series, with q being 1 over 10,000. So what we can do is rewrite this as 1055 times the infinite series of 1 over 10,000 with powers going from 0 to infinity. And what I did, I added the 0th term, which is the number 1, so I have to subtract that to make this right. And if I do that, now I can apply my geometric series formula. Now I can simply say that this infinite sum here is 1 divided by 1 minus 1 over 10,000. If I do that, what I'll get is 1055 multiplied by 1 over 1 minus 1 10,000 minus 1. If I calculate this, this is 10,000 over 9,999 minus 1. That will give me, so let me just give you the partial results. So this is the first this fraction is 10,000 over 9,999 minus 1. So that will give me 1 over 9,999. So that gives me 1055 times 1 over 9,999. Okay, so if you have entered 1055 divided by 9,999, you got it right. Okay, so for our next example of an infinite series, I want us to consider the very important series that you get when you add the sums of reciprocals of natural numbers. So this is my second example. The first one was the geometric series. This is called the harmonic series. Okay, and it will be the following series, the sum of reciprocals of natural numbers. Okay, this is the harmonic series. But let's just start writing out its terms. It's 1 plus a half plus a third plus a fourth and so on. So you get the idea. Well, let me just show you that this infinite series will diverge to plus infinity. So this is a surprising fact. It's not obvious at all that this infinite series, the partial sums, taking the reciprocals of natural numbers up to some number, will diverge to plus infinity. as the number of terms goes to infinity. So let's see how it's done, how we can do this. But let me just continue for a few more terms, and then you'll see the trick that can be used to, and so on, to see that indeed we can turn this into a smaller sum which diverges to plus infinity. So this sum, which has greater partial sums, has to diverge to plus infinity as well. So what I'll do is I'll group the terms in the sequence in a clever way. I will take 1/3 and 1/4, group them. I will then take the next 4 terms and group them. So you can see, well, I might as well have said that I group 1/2 just by itself, then the next 2 terms, then the next 4 terms, then the next 8 terms. You can imagine what's going on here. I'm always grouping powers of too many terms. So what I can do now is I can basically say that this sum is definitely greater than if I just take 1 plus 1/2, and then in my groups I always replace every term in the group by the smallest term in that group. So what I'll do here, I will replace 1/3 by 1/4. I will have 1/4 here, and then I'll do the same in the next group. I will take all terms in that group, and I will replace all terms by the smallest of these, which is 1/8. Now the idea here is that, of course, I have exactly 4 1/8 here. I have 2 1/4. So what this will be equal to? Well, of course, now in the next group I would have 1/16, 8 of them. So you can imagine what's going on. What I can say now is I have 1 plus 1/2 plus 2 4th, which is 1/2 again, plus 4/8, which is 1/2 again. So what you see here is I turn my sum into a smaller sum, which is to add infinitely many halves. But this, of course, will diverge to plus infinity. So what I should, I could, I guess, use these, just indicate that these groups turn into halves. So what I can say that this diverges to plus infinity. Therefore, the sum, that is the harmonic series, the sum of 1/k from k equals 1 to infinity, is divergent. And it diverges to plus infinity. Okay, so this is a very nice result that we have proved here. What I would like you to do now is to look at this harmonic series and tell me so your task is now to look at S16, the 16th partial sum of this harmonic series, and tell me which number is it going to be greater than. Using this estimation, what we did here, using the same technique, pause the video and give me the estimate for S16. Okay, so I hope you paused it. Basically, what I asked you to do is just consider the next 8 terms and do the same sort of estimation, giving a lower bound of another 8 of these 1/16, giving me another half here. So what I would have here is 1 plus 1/2, plus 1/2, plus 1/2, plus 1/2. I would have 4 halves. So that would give me 2, 1 plus 2. So that is certainly greater than 3. Okay, so this was our first video to the study of infinite series. I hope you enjoyed this one. I hope you got these right, and I'll see you in the next one.